fighter is maneuvering and flying at some really awkward angle, like 45 degrees. And then the pilot all of a sudden say, oh, my airplane stalled. Stall. What does that mean? No lift. No lift. The plane just plummeted. What happened is, that's due to full separation on that wing, on the airfoil. And what we're going to examine is in a very fundamental way, again, using just a fat plate. You know, you're going to sit there and say, nothing that you know of in the real world in terms of engine device look like a fat plate. Yep, I agree. Even the car hood is not fat plate, let alone an airfoil. But all these are just fundamental geometric shape to build the basic, the concept. And once you have that idea, then in your actual job application at Boeing or Lockheed Martin or Northrop Grumman, you use some very sophisticated tool, computational fluid dynamics, and you try to understand how the flow behaves. But the fundamental concept is very critical for your judgment to see if that solution you get from the computer is either correct or not correct. And that's what you get paid for to do. So what we meant by full separation is best illustrated by a boundary layer with a pressure gradient. So far we always talk about upstream and downstream pressure are the same, and that's very simplistic. Car hood, with the exception of the windshield, can be approximated as a boundary layer with no pressure gradient. But most objects, a baseball, a chimney, the flow around those devices will have a severe pressure gradient. On this device, this is not a fat plate. The flow goes on the pressure and suction side, has severe pressure change that led to this discussion. Some of that pressure change is actually beneficial. It helps keep the boundary layer attached. But there are others, which are opposite, that will cause the boundary layer to peel off or separate it. And you can't see it. This is all FO. Unless you put some dye or you put some smoke, you have no idea that the boundary layer actually have peeled off from the surface of the airfoil. And when that happens, the airfoil is not designed for that kind of operation. And the pressure on the upper surface, the suction surface, and the lower surface change so much, all the lift is gone. And it's called stall, because now the airplane is plummeting. On the turbine engine, similar phenomena can occur, where the flow can separate on the airfoil, except it's not a single airfoil, it's an array or cascade of airfoil around its circumference. And if one set, 2 or 3 blades separated, then they influence the flow on the adjacent blade and can cause the entire engine to stall. Where if you go on YouTube, you have seen some pictures where the frame, the fire, is coming out from the combustor of the engine to the front of the engine. Very spectacular. But you don't want to be on that commercial airplane when it happens. And it happened before, on the 747. All right. So all this separation is very important for us to understand how it occurs and how to prevent it. What can I do as an engineer to try to mitigate or prevent that from happening? So we start with the baseline, which is what we've been studying so far. And by that I mean the case where we assume the pressure gradient is 0. So on that, I have a solid surface. I'm going to sketch the velocity distribution for this baseline, and I'm going to compare that to other cases. So like the boundary layer, I have a small u. What is the small u? That's the name. Can someone tell me? And the distance is y vertically. Small u is what, nomenclature-wise? Small u. Is the axial velocity, parallel to the flow, that is, axial velocity. As a function of the height from the boundary layer, that's the small u. So if I'm at the wall, what is u? 0. We call it low slip. If I am far away from the boundary layer, or maybe at To be more specific, if I'm at the boundary layer thickness, delta, what is small u in relation to the cap u? 0.99, close to 99% of the free stream velocity. So u is now our nomenclature to designate the axial component of the velocity parallel to the flow direction. So for a case where what we have studied it, zero pressure gradient, if I call upstream and downstream 1 and 2, I have P2 equal to P1, P1 being the pressure upstream away from my downstream location. So on the fat plate, they're not subject to any downstream pressure variation. Then P1 equal to P2, I have this basic profile of which I will study relative to two other cases, which is what happens if the pressure is actually dropping in my axial direction or so-called streamwise direction, versus the opposite case where the pressure is actually increasing as the flow goes downstream. All right, so that's the basic. Any question on the nomenclature so far? The next case is dP dx, pressure in the direction of the flow, x is the streamwise direction, is actually negative. Negative meaning if I have P1 as an upstream pressure, and now I have P2, which one is greater? Based on this so-called dP dx being negative. Which one is greater? Yep. P1, because this said that in the direction of the flow, the pressure is dropping. It's negative. So it's 14 psi at P1, or maybe a 10 psi at P2. Right? So qualitatively, we want to ask ourselves what happened to this velocity profile that I have as a baseline, which I will sketch as comparison here. So this is the baseline velocity. And now I want to superimpose on that how this pressure gradient, well, is dropping in the direction of the flow will influence this profile. So to do that, let's look at a very small fluid element inside the boundary layer. This square, dx dy. If P2 is less than P1, what is the net pressure force? Which direction? Acting on this element. To the left or to the right? You all agree, right? Because the pressure is actually dropping. So the net pressure force will tend to take this differential fluid element, and due to this net pressure force, it's trying to push it to the right. So if my baseline is shown here, how would that change this velocity profile due to this added net pressure force? It will take this profile and move it which direction? To the left or to the right? To the right. So I have now a new profile that is due to this pressure gradient, or less pressure downstream than upstream. We'll give a name to that. First, this represents pressure is dropping as I go downstream. And we'll call that, for reasons that become clear later, favorable pressure gradient. Favorable, I mean I like it. It's good, something that I'm happy with. So tell me some engineering devices that you have learned from both fluid and thermal, of which overall the pressure from the inlet to the exit is dropping. maybe some devices that you know where coming in pressure is 30 psi, coming out the pressure maybe 15 psi or atmospheric.
Diffuser.
Okay, beyond that, I know you're considering nozzle diffusers. It's a little more complicated. Think of something even simpler. How about a turbine? A hydraulic turbine or air turbine or any kind of turbine, of which pressure is dropping. Right? In all your thermal calculation, isn't that what you see? Correct? You with me? Water turbine, the same. The gravity height head is being fed as a higher pressure through the turbine and mixing an ambient pressure. The other device is actually a nozzle, not a diffuser. A nozzle, as I remind you, is a device that the area is getting smaller because it helps to accelerate the flow, like in the aircraft engine nozzle. So you have very high momentum fluid coming out. And how do I know in the nozzle the pressure actually goes up? Bernoulli, yeah. If you can just simply apply Bernoulli in the implicit frictionless region of the nozzle, then immediately you conclude as the pressure, as the velocity speed up, pressure has to drop. So those two devices is what I call favorable pressure gradient. And it turns out it implies that it's less likely that the flow will separate. And I'll give you the counter example now as to what will cause the flow to separate. And then you can compare them. So I'm done with the favorable case. Now let me tell you the bad case. So same comparison with the baseline. Now I have a different pressure distribution, where as I march downstream in the direction of the flow, the pressure actually goes up. So I have here pressure increases as I go downstream. So the same boundary layer now has to be subject to a little bit different pressure force. So the same element of dx dy in my boundary layer, because of the new pressure distribution upstream and downstream, which direction will the net pressure force be acting on this element? To the left or to the right? It will be opposite from what we did before, right? So which direction will it be acting? Pointing to the left. As a result of that, this baseline boundary layer profile will be pushed towards which direction? To the left or to the right? To the left. So I have now all of a sudden a boundary layer that look rather odd. They look kind of like this, where near the wall I have, in the limiting case, a point of inflection. And the fact this profile is being pushed to the left is simply because of the pressure acting in the diagram shown here, which is against my momentum. It tried to slow me down. It will be me marching towards that wall. Every step I take, I have more and more resistance due to the pressure increasing downstream. And remember, in the boundary layer, I'm already tired. In the free stream, it may be 100 feet per second, but in the boundary layer near the wall, I have zero momentum. Close to the wall, I'm tired 10 feet per second. I take one more step, there's more pressure pushing me. What I would do as a tendency is I would stop. I just say the hell with it. I'm not going any further. I'm tired. I'm not going to march one more step. If I do, this is what happened. As I get closer to the wall, the force due to pressure is so much, I actually go backward. I'm being pushed backward. And the boundary layer now become separated. So this invisible layer all of a sudden can become very big, because no longer it's a boundary layer. The flow is now completely separated. And to illustrate that, if I have an airfoil that's very well oriented to the flow direction, meaning the airplane is cruising nicely and steadily, the flow and the pressure gradient around the upper and lower surface is such that the boundary layer is attached. It's very well behaved. And my design of the airfoil shape, by intent, allow this boundary layer to remain attached under cruise condition at relatively small angle attack. However, during the dogfight, all of a sudden, I'm coming at an angle attack of 40 degrees. So the flow is no longer parallel or tangent to the leading edge of my wing. And the pressure gradient created on the upper surface, and what do we call that surface? Anyone remember? Upper, lower, but there's another term that goes with them. Suction surface. Pressure surface. All of a sudden, this pressure gradient of very severe downstream increase caused the boundary layer to peel off. I'm so tired after a very short distance on the suction surface that I just let go. I just go backward. And this is where stall occurs. Because the airfoil is not designed to generate any lift. When you have this flow that's invisible to our eye, but completely destroy the pressure distribution as our design intends. That's what we're talking about in here. So this is separated flow. We call it both cases where the pressure is increasing downstream. We have a very peculiar name for it to remind ourselves that we're dealing with some very dangerous situation where all hell can break loose. So these cases of increasing pressure downstream is what we call adverse bathing. Anytime you see a pressure increasing in a device, as you march downstream, you have to be on alert because it can bite you. So namely, two devices for engine application that you see that, where pressure at the exit is higher than the inlet. What's the counterpart of the turbine? Compressor. Or pump. That's why compressor efficiency is in the upper 70%, or at most 80%. And so it's pump, but for a turbine, you can reach in excess of 90% because of all this potential for full separation. Okay. Another device that will have pressure increasing as you go downstream, what is the opposite of a nozzle? A diffuser. So the diffuser, where the velocity is dropping, like that in the inlet, like that in our wind tunnel where the flow after the test section has to open up, is very dangerous where the flow can peel off at the wall and separate it. So there are ways of help to combat some of this separation in some of the much older airplane on the wing. So here's a fuselage. On some of the old model airplane, there are tabs on the suction surface of the airfoil. They don't do that anymore. Any idea as to why that is needed? It turns out those small tabs help generate some vortices in 3 dimensions and help to energize the boundary layer so that they can overcome or withstand those pressure gradients without separating. So that would be a good point to end the lecture by giving you one more food for thought as to the difference between a laminar boundary layer versus a turbulent boundary layer, as to which one is able to withstand this pressure gradient better. A turbulent boundary layer, because of the randomness and the unsteadiness, that's chaos in the flow, inherent in the flow, can withstand separation better than a laminar boundary layer. And I will come back to this next time to repeat this very important observation. And that is why impulse is put on a golf ball to make the boundary layer turbulent. So that's the subject for next lecture. So I will come back to this next time with qualitative observation of how boundary layer, turbulent versus laminar, have the impact on flow separation.
Yeah, I was just wondering what